In this video, we'll be discussing about input impedances. Now, let's just assume that ZO and ZL are set here. Alright. The input impedance is the impedance when we look at somewhere. So the input impedance when we look at the load is of course the load. Alright. But it's going to be different when we look at it here or maybe at the source. Why? Because of the standing waves, remember? So the standing waves can vary by a lot, right? There is a Vmax, which is the maximum amplitude. There's also the Vmin, which is the minimum amplitude, right? So if there are standing waves in our graphs, if there are standing waves in our transmission line, it means that we have a varying input impedance. So it also means that if our input impedance is the same everywhere in here, then that means the standing waves would have, well, it wouldn't change. And since standing waves change, they wouldn't exist. So if the input impedance was the same everywhere, then it means that there is no standing wave. Alright? When does that happen? Well, if we had to guess, it would happen when ZO and ZL are matched. But let's try. The formula for the input impedance is ZO and then multiplied by this insane looking fraction. We put ZL and then ZO here. And then we add them by ZO hyperbolic tangent of gamma S. I don't have space to put it here. Over this hyperbolic tangent of gamma S. Hyperbolic tangent is a really alien function in here, but it's all gonna work out in the end. Now, gamma. We've seen gamma before. Gamma is alpha plus j beta. Remember. Alright. Alpha is the attenuation constant. This measures the amount of loss or the amount of heat being dissipated away through the wires instead of being dissipated at the load. This is the phase shift constant. So yeah. Now, in order to simplify this, we can take hold of the fact that the tangent of something imaginary, for example, hyperbolic tangent of j theta, that is j tangent of theta. And we have something j beta over here. That's the only thing interfering with, that's the one thing that can make this much simpler, and instead of hyperbolic tangent, we would have tangent, right? But there is the alpha. So, in transmission line theory, what we do is expect alpha to be equal to 0. This means that we have to expect that this line is lossless, meaning the transmission lines do not radiate power outward. Instead, what we want is the J beta or the phase change. So we imagine that it changes phase. So, let's change the formula now. So Z in equals ZO, ZL plus, okay. So omega becomes J beta now. And since tangent of J beta S, that is an imaginary number on the inside, we have to turn it into J times tangent theta. So J times ZO tangent of beta S. Remember, beta S is the angular distance. So that's good. Over ZO plus J ZL tangent beta S. There we go. That is the formula for the input impedance of the transmission line. So we have a few parameters here. Of course, ZO and ZL are set by the system that we want. And then beta, again, is 360 degrees over lambda, which is the wavelength. And then S is the physical distance. Sometimes we use electrical length or the amount of wavelengths a certain distance has. Then we multiply it by the wavelength. Okay, so this essentially means how many wavelengths does this distance have? And if we multiply beta and S together, we can notice that we can cancel out the lambdas in order to get 360 degrees times electrical length. And that's it. So that's beta S. Alright, so from here, let's derive a few formulas from the base case. Firstly, what if we had no load? What if it was shorted instead? Alright, what would happen to the wire? So in here, ZL is 0. Right? So anything with ZL in it gets eliminated. So cancel that, cancel that. We only get ZO times ZL is gone. So what remains is ZO tangent beta S over ZO. So this and that cancel each other out. We are left with ZO tangent beta S. Alright? Now, that's the first case. This is shorted. Next, what if instead of shorted, this was open? In this case, ZL would approach infinity ohms. Alright? So when we have ZL as infinity ohms, we do have to do some little math in here, specifically calculus. So, if the limit of ZL approaches infinity, in here, we can safely ignore ZO and ZO over here, right? Because ZO would be very, very small and ZL would be very, very huge. So ZL would safely be on top. So Zin equals, ZO would remain, but the ZOs in here would not remain. So ZL over JZL tangent beta S. If we then cancel the ZLs, we would have Zin equals ZO, characteristic impedance, over no ZLs now because we've cancelled it out, tangent beta S. This is the open case. Alright. Now, let's look at it another way. Maybe there is a load here, but our distance is here, which is going to be half a wavelength away. Alright. So what will happen if our distance, and if we try to find the input impedance from half a wavelength away? Well, that's where this S comes in handy. That's going to be our, so beta S in this case is 360 degrees over lambda times and half a wavelength, that would be 0.5 lambda. Cancel the lambdas, multiply 360 by half, we get 180 degrees. Tangent of 180 degrees, if you know, is 0. So, tangent being 0, we can remove any term in here that has tangent. So remove that, remove that. We're left with ZO times ZL over ZO. We can cancel the characteristic impedance and we get Zin equals the load. For S equals lambda over 2. Now, this actually means something very specific in transmission lines, which is the input impedances of a certain point. For example, you know the input impedance in here, which is location S. That the input impedance at S plus lambda over 2, or half wavelength away, is going to be the same as the input impedance looking in here. the input impedances would be here looking the same because they are lambda over 2 away, right? And S equals lambda over 2 is a special case because what is lambda over 2 away? That is going to be the load. So the impedance looking at lambda over 2 away would be the same as if you were looking at the load itself. So that's what that means. Next, let's look at if lambda is by lambda over 4, lambda over 2, 4. So this would be quarter wavelength. What would be the formula then? All right, so beta S at this point would be 360 over 4, which is going to be 90 degrees. Tangent of 90 degrees approaches infinity. So this tangent BS, beta S, would overwhelm the other terms. So we can cancel out the ZL and the ZO here because they are, well, not infinity in this point. If we cancel them out, we are left with JZO tan beta S over JZL tan beta S. So the next case would be Z in equals ZO times ZO, so that's ZO squared over ZL. And the tangent beta S and the J would cancel themselves out. This is the case for lambda over 4.